Hi, welcome to the Signal Path. I have yet another repair video here. This is the last piece of equipment that I have lying around for repair, so I'm sorry for the long sequence of repair videos. I'll get back to doing regular tutorials, and I have a bunch of really interesting topics as well as some interesting product reviews coming up next. Hopefully my schedule will allow me to produce them quickly. But here we have here an HP or an Agilent EPM-441A. This is a power meter. This is a single channel power meter. I do have a power meter in my lab also, but that's a dual power meter, and also that was actually branded as an Agilent one. That's an E4418B, which is a newer model, and we'll take a look at that, and it would be a good thing to have as a reference when we're taking a look at this, because the schematic of this is not available. And this is actually quite a bit older, but it shares the same front panel. It looks essentially exactly the same, except for the fact that the two-channel version has another input available here where you can connect two power sensors to it. So obviously these guys use the external power sensor, and there is a reference 50 megahertz 1 milliwatt, which is a 0 dBm power generator, which is calibrated. So this is how you calibrate your power sensors, and we'll talk about how power sensors work and all that in general. As you know, whenever I do a repair, I also do a bit of a tutorial on something about the unit. So perhaps for this one we'll talk about how power meters and power sensors actually work. So this one I picked up from eBay for a fairly inexpensive price because it was not working. So let's power it on and see what's wrong with it. There we go. I plugged it in. You can see the light turn on here. This has a soft power on button, so it's in standby mode right now, and this is typical for these power sensors and power meters, and this is because some of these models, although this one is not equipped with that, has a crystal oscillator that has an oven controlled component on it, which has to be always powered on, so that when you turn it on it's already calibrated, sitting at 1 milliwatt. So they keep a portion of the circuit at temperature for accuracy of frequency as well as the accuracy of 1 milliwatt output power, because everything will ultimately be done with respect to the 1 milliwatt calibration power that comes out of this. And if you can fix that, we'll have to see if that can be calibrated and if it can be adjusted. So now if I go ahead and power it on like so, and this is all that it does. I can hear a fan turn on inside the unit, and of course this display is showing absolutely nothing. You can see that the contrast shows up a little bit at the back, and I couldn't see anything on it, and none of these buttons basically do anything. I've tried powering it on and off while I'm holding one button, for example holding this reset button, power it on, and nope, nothing. And I looked at the manual, but there's nothing specifically about that. There is no data sheet for it, there's no schematic for it, so there's nothing that I can do. So unfortunately, when I bought this, I thought that it just didn't power on. I missed the fact that it does power on, and it shows this. So we are again dealing with another instrument that has potentially some firmware problem because of the fact that it gets to this point and it doesn't do anything. Or it could be that none of the processor is running and this is just a backlight turning on, and that's another possibility. So the only way I can find out is to get some further investigation. But now if you take a look at the back of the unit, actually, let me unplug it and turn it around, you will notice that it does not have a serial port or anything like that. So all the communication is handled through the GPIB port, and the GPIB port doesn't do anything because the instrument doesn't boot at all. So I have no way of accessing the firmware unless I open it up and see what it looks like on the inside. So that's the next step. Let's go ahead and see what it looks like on the inside. I have opened my own unit before, but this is a much older one, so I don't know if it looks the same. Alright, I took these off, and actually one of the reasons I bought this is because it included these soft legs on them, and these are sometimes people take these off the instruments when they want to put them in a rack, and then of course they throw them away and discard them. I always tend to buy equipment that have these because I like to have these nice ones. They're good when you put these on a bench. So now everything else is pretty straightforward, and I think I should be able to actually remove it. There we go. Should be able to open this. Let me see. Make sure you get a good view here. There we go, and aha, look at this. It doesn't actually look like the one that I have. It's a little bit different. This is a much older construction, and you can see again shielding around the edges and the inside, conductive tape here, which has some spongy material in it to protect it from any kind of EMI going in and out, to shield the instrument. This general practice, you've seen this, and I've showed it many times before. So here we go, and Well, I'm looking at this for the first time here with you guys, so we can walk over a couple of things. You can see it actually has quite a bit of modular design. I can tell right away that this board is obviously connected here with this ribbon cable to the front, so it's connected to this front connector here. And the way this board is designed, here we go, you can see that this board can, yeah, it can likely come out, it will come out, and then if the other connector here is populated, which is not right now, then you would be able to put another board, and it looks like even a third board here can be plugged in, which is interesting. I wonder what that would be for, because I don't think this can come in more than 2 channels. So then another one of these can be plugged in, and then that will be populated, you plug it in, and then you'll have 2 ribbon cables coming out, and then you can have 2 channels in the front. That's what the difference would be. So they've designed it in a modular way for you to be able to put multiple cards in. So I don't think the problem is with this card anyway, because we never even get the instrument to boot up. So we never reach a point where we are accessing the DAC and the readout board that is here. So forget about that. It's interesting that there's a crystal here on this board, and there is a room for another. It says that's just I was reading this DAC cable that appears to be just that little solder mask test point right there. But I don't know what this is. It perhaps some other module which can be fully shielded. That can be maybe an upgrade to an existing one. But everything else is pretty straightforward. And there's a crystal here. So I'm gonna take this out anyway. We don't think we need it. On the front you can see the display, the back of the display, and a whole bunch of circuitry there. Here in here. There is a shielded protected section. This is the 50 megahertz generator, which is connected with this cable and is connected to the front right here, and that's how it generates the 50 megahertz 1 milliwatt standard calibrated outputs. And there's 2 holes on there, which I imagine are the calibration points. So that should be interesting. From the look of this, I say that's an inductor, a variable inductor, so that's probably to tune the frequency, and that looks like a screw for a potentiometer, and then most likely the output power. That is in the ALC loop, so there is a power detector in here, and you can adjust the reference to the power detector and then adjust it in the feedback loop to keep the power constant at 1 milliwatt. And that's what, likely, in my opinion, that's what that does. There's a battery in here, and if you take a look at the back of the unit, let's see, what do we see? Whew, look at that. There's a nice board there. Absolutely no components at the back. A bunch of solder masks and a bunch of little marks on it, nothing special. Here's the back of that 50 megahertz reference generator. You can see a cutout in the board. This cutout is here so that you can put a wrench in there and disconnect and unscrew that little screw there, which has a rigid cable connecting from this to the front of the instrument. That's there for that reason, not for isolation or anything like that. It's just to you can get a wrench in there for that purpose. There's a connector here which tells me that this board is standalone, so this is actually made of multiple sections. So here's the board. This board, the back, connects directly to the back of the instrument, and it looks like that is the board that controls all the communication from the GPIB to the board, and there's a bunch of unpopulated stuff I can see. So perhaps there is a serial port interface on this, it's just not populated. That would be an interesting thing to take a look at also. There you go, I took that opportunity to grab my pen. Some of you guys have asked me what this is. This is a metallic pen, it's a scourging pen used to mark metal. If you do any machine working, this is a very common tool that you would find. Sometimes, not for this one because it has a very fine tip, you can put these on top of a piece of metal that you want to drill, and you tap a hammer in there, it makes a small mark on there, which allows you then to put your drill bit on there, and the drill bit wouldn't slide around. It's like a mark for you to start drilling on a metallic surface, and that's some of these pins, but this is not for that purpose. But anyhow, you can find these if you have to go work in any machine shop, and this is from a machine shop I used to play around in. Anyhow, so let's take a look here. And what else I was going to talk about. So there's a connector here that connects these two. Unfortunately, from the way this is constructed, we have no access to any of the components on this board. Although I do see some things called system clock, for example, on here. There's 0 volt references and a couple of volts. The system clock would be an interesting thing to check, because it could be one of the reasons why it doesn't boot. If the processor, the main firmware processor, has no clock, obviously nothing will boot and only the display will turn on, and it won't. And actually there's an LCS boot. I don't know what that means. There's a memory LOE. There's a bunch of this. There you go. Here's our power supply voltages. It only runs from 12 volts, minus 12 volts, plus 12 volts, and 5 volts. So it should be a very, very straightforward otherwise. But I would like to take it apart, even if even if you find a problem, we cannot really fix it because most of the board is underneath. I only see the front of the board here, and I don't see any processor or any memory or anything like that on this side. All I see is a bunch of inductors here, these ones which are perhaps for some filtering, a big capacitor here. This, I think, what is that? Oh, that's the fan. There you go. That's the fan that's sitting inside the power supply. And here's the power supply connector coming out. So the power supply is under this shield, and you can see there's a warning, hazardous voltage there. This ribbon cable looks to me to be the keyboard, and or maybe not. This ribbon cable maybe the display, and this ribbon cable the keyboard. I'm not sure. One of those two is to control the buttons, the other one to control the LCD screen. So everything else is pretty self-explanatory. So we can go ahead and start trying to take some of these apart. Let me see. I can take that, for example, out. There we go. That was pretty straightforward. I should be able to slide this out. Is this going to come out? Or am I have a really awkward angle here. There we go. Not bad. There it is. Again, close look at this. Again, I assume this is a crystal of some kind, and it likely is from its footprint. I don't know why they would have a crystal here. I'm not 100% sure. There is a bunch of solder masks here called gain and sense and a bunch of things like that. So it's actually fairly well labeled, even though it doesn't have, I don't have the schematic. There's another system clock, buffered system clock in here. So it's beginning to make sense to me what that system clock issue is. So they likely generate a clock and they pass it around all throughout all the modules. So this module will then all run coherently with the system clock that's sitting on the board itself. I don't know where that system clock module itself is, the crystal, because I don't see it yet. It's not in the front of the unit. And the back of this has a, whoa, look at that, so many passives. My goodness, so many capacitors and resistors. Nice layout. Looks like it's auto routed from the look of it, but anyhow, looks pretty nice. An analog devices part in here, a DSP, I'm not sure what that is. There's a Xilinx part here, something that has to do with the firmware, and a bunch of other components. I don't think it's very interesting to go into too much detail in here, but anyhow, looks nice. It's a nice little board, so we're going to put this aside. Again, I don't think the problem is from this because it doesn't even boot. This is just for the channel. So if the channel had a problem, then we could say, okay, this is an issue. But if we don't even get to the point of even reading anything, so this is basically has to sit on the side for now. Let's see, what else can we take apart here? There seems to be two pads here. Is this going to come off, or am I just... Oh, there we go. There you go. Ah, that's nasty. That's just a lot of dust in here. Again, remember, this is a really old unit. Here's the power supply. Most definitely not made by Agilent. It's made by Computer Products. I think I've seen this brand before in other Agilent and HP equipment. It is a classic single layer switching power supply, nothing fancy, with a fan in front of it that blows air constantly into the power supply to cool it down. The cables that come from the main plug to the AC voltage at the output are very nice and short. You can see nice attention to the ground. The ground comes there to the chassis with the rigid washer to make sure it makes good contact, and then back onto the power supply itself. And then the two of them very short cables, and these are isolated. So if you don't touch this area, you're actually quite safe with this unit. I don't think you can injure yourself in any way or electrocute yourself. But anyhow, this power supply likely works because we do see it power on. And this cable here that's coming out, going in there, what is that? That's the recorder output. Not 100% sure what that is. Perhaps an analog voltage that's connected directly to the sensor. But there's nothing else at the back because you could have this thing populated with an option where the controls instead of the front are at the back for a system setup when this is in a rack, but this doesn't have that option. Not that that matters, but look, if you look closely in there, you can see there is what appears to be a 9-pin connector. There you go, that's our serial port, and it's not populated. And there is most likely the voltage level converters for the serial port from TTL to serial levels, plus or minus 15, I believe, or plus or minus 12. And those are not populated because this doesn't have that option. So worst comes to worst, if we get to a point where we think that is working, but everything else is, we can go through all the trouble of putting that on. I hope we don't have to do that. Another thing I noticed is that this thing is built like a tank. There is metal everywhere, multiple layers of metal, very thick pieces of plates here. It's quite heavy for its size, but I can see, I was looking at it when it was turning around, you can see these notches here. So this board should be able to slide forward, but of course it cannot slide forward as long as this front panel is connected. So Well, one thing we can do is we can, now that I've disconnected this, although that wouldn't matter, and I've pulled this out, we can try and powering it on one more time, just to make sure that that wasn't causing some kind of a short. And carefully plugging this in, not touching anything. Let's see. There we go. Turn it on. No, does exactly the same thing. Nothing. Oh, wait a second. Oh, I just noticed something. Haha, look at that. Oh, sorry, this must be a really weird angle for you. But look at this. Ah, you see that? If you look at it at this really sharp angle, because of the weird contrast of the display, I couldn't read this before because I was looking at it right side up. This is basically, now we're looking at it from the bottom of the unit up. Look what it says. It says starting main firmware. See that? Ha, that's a new discovery. So it's stuck somewhere. There we go. We have another, I can't believe that I have another instrument with a software problem. This is the second one in a short amount of time. So yeah, so from this angle you can't see anything because of the contrast, but as soon as I tilt it, now you can see it, starting main firmware. So it's actually stuck. That's interesting. So the processor is working. Oh, look at this. It's a Christmas light. Haha, that's kind of cool. You can see the backlights from the back of the unit. Ooh, it's back LED backlight, completely covering the back of the unit. That's interesting. This is probably one of the very few fully LED backlight displays from so long ago. Pretty interesting. Anyhow, so it is indeed starting, it's just stuck. So that's something that I just discovered. Well, this means that we really do have to take it apart because most likely all the power supply voltages are fine, but anyway, I will measure it again. I'm going to try and take this off so that we can take the bottom board out, and if I take the bottom board out, we can then have it laid on a table and just power it on and then be able to look at it without all the metallic case around it, and that way it's the bare bone main PCB, and then we can see if it still says firmware loading. Maybe that's a good starting point. So here's the display unit. I took it finally out. It was actually quite difficult to get this out. It wasn't screwed in, it was held in position by the pins that were extending through these holes on each side, so you had to kind of flex and bend this to get it out. So not the best manufacturing process in my opinion. But here you go, you can see the ribbon cables. Here's the ribbon that feeds the display, and here's the ribbon that connects to all the buttons in the front. Here's the input for the output, I should say, of the 50 megahertz reference, and here's the connector for the reference input from the power sensor itself. So this is I actually didn't disconnect the cable from the unit itself. I disconnected that. It was easier for me to unscrew this SMA than to unscrew that, so I left that in there. But you have a better idea of how it's manufactured. So I can go ahead here and disconnect the fan and disconnect the power supply cable. There we go, I think so, there it is. So these two are now coming out, and this piece of plastic should slide forward, and then we should have access to the board. Here we go. You know what, it has 3 screws on it. I didn't realize that, so I can't just slide this out yet. Alright, let's get the proper screwdriver for this. Here we go, I'm sure I have the right one. I think this might be it. Let's see. Here we go. So yeah, there it is. That's the right one. And we should be able to get this board out once we get rid of these. Let's see now. I expect this to slide forward. Wow, it is really stuck in there. Let's see. I have a bad angle here. It's actually quite difficult to operate. The camera's in the way. There we go. I think it's moving. Nope, not yet. I don't think there's any other cable. Oh, you know what? Geez, look at that. That was a stupid mistake. Of course it's not gonna move because this is still in here. There you go. This should come out. There it is. Yeah, so this is the daughter board connector. So basically this allows a vertical connection to be connected to the motherboard. It's nothing more than basically creating a 90-degree angle between the main motherboard and the other board that we saw. So this of course then plugs into here like so. So we've seen those. So put it aside. Here we go. Now it should be free. I don't think there's anything else holding it in place. There it is. There you go. That's much easier than I thought, like this. So now we should be able to take this guy out and then take a look at it. There it is. There we go. Here's the rest of the stuff that we were looking for. So what we have here, it's interesting because I can see some labels on the PCB here. Let me flip it over. So here's an Altera part, which likely is holding some kind of firmware. I can see here it says high flash, low flash, and there's battery backup RAM. Here's some RAM here. Here's a microprocessor from Motorola. Here's our clock. There we go. 16.67 megahertz written right under. That's our main clock. There it is. Look at this clock distribution. So here's our clock distribution IC, which then buffers and I guess distributes the clock all over the place. There's a bunch of unpopulated parts here, which I assume is because this only has one of the two channels. Perhaps that's one of the reasons, and a few other components here. So it's a really, really simple architecture. We should be able to take a closer look at this and figure out what everything is. But first of all, let me just power it on from an external power supply, connect a display to it so we can just work on this directly without this massive piece of metal here in the way. And this is nothing else on it. This is the extension board, which has the GPIB and the serial port stuff on it. Here's the power supply. We don't really need this. I assume all of this is functional, so we can focus on the main motherboard. Here we go. So everything is taken out and connected. So what I have is the power supply being emulated from an external power supply, so I don't have to have its own power supply connected because it was a hassle and the cables weren't long enough. So I'm using the Rigol DP1308 with a tracked tracking generator between the 25 and minus 25. So they're set to plus and minus 12 volts, and the other one is set to 5.2 volts. So you can see that right now in standby, the reason I set it to 5.2 volts is just because there's going to be some drop in the voltages from the 5 volt supply, and that's going to eventually make it about 5 volts. So 5.2 is okay. And you can see that there is a little bit of current being drawn from a plus and minus 12 volt supply, and almost nothing, only 3 milliamp from the 5 volt supply. And the unit itself is behaving like it was when it was connected to the external power supply. So if I go ahead and push the button, you can see that it powers on, and it actually is still displaying the same message. It says loading firmware where it is stuck, and you can see the power consumption here. Oh, let's see, about 900 milliamps or so. So if I go down to 5.1 volt, for example, it drops to just below 900. But we can go ahead and do a quick measurement in there just to make sure that all the voltages line up and that we are indeed giving it what it should be, even though from the digital power supply perspective it shouldn't matter so much if we are off by 100 millivolts or so. So I'm going to use this Keithley 2015, which is actually a THD multimeter, but anyhow we don't care about that aspect of it. But it is a very good multimeter, and it is calibrated, and this is the ground and this is a 5 volt, and you should be able to read it there. You can see that it's exactly at 5 volts now. So I'm giving it 5.1 volt, it is getting 5 volt, which is due to the drop of course in the cables itself, because I don't have the sense enabled. So it looks all good. So now the question is, what is happening? Well, we're gonna have to do some reverse engineering to figure that out. So if you look at, here's the microprocessor here, and the microprocessor and the flash memories and the RAM are all connected together, and there's also some connection between that and the Altera. Now I suspect that the Altera here is just basically some glue logic. I think this is a CPLD, and it's only used to basically make some connections between various components. It's not the main, obviously, core processor of the unit. The core processor would be this Motorola unit. And what it looks to me is that the Altera, for example, could be responsible for driving the display and communicating with the display, and possibly even communicating with some of the other buffers and various components that interact with, for example, the board that sits on top of here, and even interacting with these memories. Now it's interesting because it says loading firmware, but it doesn't work, and obviously it has to grab the firmware from the flash memory. So it looks to me that the microprocessor is trying to grab the flash memory and possibly putting it either into the FPGA or into the RAM before it starts executing. It's a little bit strange why it is done that way, perhaps because this Motorola doesn't have enough memory of its own, so it needs external memory. So unfortunately, if the flash memory cells here are broken, there's nothing we can do, because I do not have the flash program, the main firmware that runs in the unit anywhere, and I couldn't find it. So even if I were to find replacement ICs for these, I wouldn't be able to program them because I wouldn't have the appropriate program to put on. But nonetheless, I would like to make sure that my hypothesis of how these things are all connected is actually correct, that this is indeed happening. So let's power it on and connect it to the oscilloscope and just monitor a couple of points around here and see if we see any activities on these pins. I'm going to go ahead and dig out the data sheet of these parts as well as the microprocessor and the Altera, and we can have a quick look and make sure there's clock appearing on the microprocessor, there's clock here, and there's generally some activity, and that should maybe give us some hint on where to look next. This is unfortunately a bad problem, and it may not be very easily fixable because of it, because it's just some software hang up, and like I said, if the flash are dead, there's nothing we can do. So let me very briefly talk about the components that are of interest, which might be responsible for this unit not working. So obviously the FPGA, the microprocessor, the flash, and the SRAM are all working together in order to run the operating system, the firmware of this unit. So let's just quickly talk a little bit about this, and this will also allow me to explain to you the strategy that I have for trying to debug this. Hopefully, like I said, the flash chip is not the issue because there's nothing we can do about it. But nonetheless, so this is a microprocessor. It's actually the MC60 8000 from Motorola, but it's a Freescale version, but it's the same thing. You can see it has a very simple block diagram. The RAM and the CPU, 32-bit CPU cores are here, and there's a whole bunch of IOs that you can see at the right side, which interact with the chips outside of the IC, and there's a clock input and so on. So one of the very first thing to check for the microprocessor is obviously to make sure it has the correct power supply and make sure it is getting the correct clock. And in order for me to do that, I have the pinout here of this package here, and you can see somewhere around here there's a clock out, and there's the external crystal and on and so on. So in this region is where the clock inputs would be. So I can have to look at it a little bit closer. For example, there's also the reset pin. We have to make sure that the microprocessor is not somehow stuck in reset mode. And once you verify that, there's the crystal oscillator input. So we can take a look and make sure that this is getting the clock. So I have the pin out of it. That should make it pretty straightforward. The other thing that we need to look at is the FPGA. So here's the MAX 7000 PLD. It's a programmable logic device. Again, it has a very simple block diagram, and this is of interest because again it has a global clock and a global clear at some of the fundamental inputs to any CPLD, and then you can check those to make sure they are functioning, and that will help as well. And I also have the pinout of that unit as well as the 44-bit PLCC version of it that's sitting inside the socket. So this tells me that this has been programmed somewhere, and hopefully the program inside the Altera FPGA is not damaged, because if that's also bad, it also will not be possible for me to fix it. So that's another thing to check, make sure it has the correct supply. And you can see it has various IOs around it, and in here are the global clock and global reset bits. So we'll take a look at those as well. Another thing I'm interested in is to try and trace out if any of these pins actually directly connect to any of the SRAM or the flash memories, because obviously either the FPGA or the microprocessor is responsible for extracting the content of the flash memory and executing it. Now I suspect that because the microprocessor doesn't have enough RAM, as I said before, it will extract the firmware from the flash memory, dump into the SRAM, and then begin execution. And as a result of that, if the flash memory is broken, obviously it's not going to be able to extract the memory, or if the SRAM is dead, it's not going to be able to run and execute the code. So one of those things most likely is the cause of the failure if the processor is working. One of the reasons I'm more inclined to think it's the flash of the SRAM is because it is showing displaying the message, loading the firmware. And if it is displaying that, it means something is alive. The microprocessor did something, the FPGA most likely did something, because the FPGA is likely driving the display, which means that is working. That's why I'm leaning towards the other components. So as far as the flash memory is concerned, the particular data sheet that I found is an AMD part, and it has again a very simple architecture, and it has write enable, chip enable, output enable pins, which we can monitor. These will be interesting pins to monitor, and here's the address bit and the data bit, because it is you can put these chips obviously in parallel, and by disabling and enabling their outputs and disabling the right input and output, you can target a particular IC and read from that IC, and that's really important. So we can take a look and see if there's activity on those pins. Again, I have the pinout of it. We are looking at I believe the standard pinout of this, because there's the reverse pinout. I'm not 100% sure, but I think it's the standard version of it. Let me take a quick look. Yeah, it is the standard version. This is the pinout we're looking at. So again, VDD is here, write enable is here, and all the data pins. So I can put an oscilloscope on this, and I should see some activity, because there should be continuous interaction between the microprocessor and the flash memory, at least during boot up. And last but not least, we have the high-speed CMOS static RAM. This is a Sony part, and it's a 131,072 word 8-bit high-speed CMOS RAM, and it comes with a different type of packages, and it is the SOP package, the plastic 32-pin package that is on this board, I believe. Again, very simple block diagram, address bar here, and the data, which I cannot see right now. Where is the data pin? Here's the address. You know what? I cannot see the data. Maybe some of this is the data. Now I'm a little bit confused. Oh, there it is. Sorry, there you go. The I/O buffer here. This must be the data input and output. Here's the full address bit, and here's the chip enable 1 and chip enable 2, and this is how you can cascade multiple of these ICs again and be able to write to them. So pretty simple, straightforward SRAM architecture. And I have the pinout as well. We're looking at this package. There's a whole bunch of pins here that write enable and chip enable right here. You probably cannot see it. But again, I'm going through this for sake of completeness. So what is my strategy? My strategy is check the clock on the microprocessor and on the Altera chip, then check, just put my oscilloscope probes on a bunch of these pins, see if there is any activity, and then go from there, see if we notice anything wrong, and hopefully we can figure this out. Alright, so I've gone ahead, connected my regular oscilloscope to one of these pins, which is ground. I just traced it out to make sure it's ground. I compare it to the ground of some of the other ICs, so this is one of the pins I can use. It makes it a lot easier, that way we can have direct access. It's a little bit long, so there's going to be a little bit of a ground loop there. Some inductance is going to affect our waveform measurements, but I really don't care. We just want to mostly make sure that the waveforms are actually there where we expect them. So let's start with the FPGA. Here's the FPGA pinout, so we can see at the bottom I'm expecting a VDD. I'm assuming this is going to run from a 5-volt supply, and the clock is at the top. And we can measure all of these things directly with the oscilloscope. So I can go ahead and kind of tap the pin here and then look at the clock there, and I have my regular oscilloscope there looking at it. So I'm going to maybe just focus on the scope for a bit so you guys can see the measurements that I'm doing. So I'm going to try and find the VDD here. Let's see if we can find that. There you go. Oh, that's not too bad. So it actually says a maximum of 5.1 volts. So the VDD appears to be there. It looks good. It's fairly solid. I don't see any major ripple on it or anything. We're on a 2 volt per division scale, by the way, and a 10-to-1 probe. Now let me see if I can find a clock. It should be the third pin from the right. So 1, 2, and 3. What do we see here? Am I looking at the right pin here? Ah, there we go. That's not too bad. Its amplitude is a little bit low because you can see it's hitting a maximum of 3.7 volt. That's a little bit strange, but I think it's still okay because it's still significantly 3.78 volts, significantly more than 2.5, which is roughly the threshold where I expect the clock to be. And the frequency is 16.67 megahertz, which is exactly what it should be. So at least the VDD and the clock are appearing on the FPGA, and that's a good sign already, which means that we are at least have some clock signal available. That's gonna be helpful. So the next thing I want to look at is I want to do exactly the same thing on the microprocessor and make sure it does have a clock. And of course the crystal oscillator is here. I should be able to just directly look at the clock of that. Its VDD is there. And is that the clock? No, that's not the clock output. There it is. There we go. So it looks much nicer coming out of the crystal. It's much bigger. Its amplitude maximum is 5.19 volts, and this is coming directly from the crystal oscillator. The signal going into the FPGA was lower, and it's most likely because it's going through this clock distribution IC, which is right here, and I should be able to measure the output of this. There you go, in a couple of places. I'm looking at it on the scope right now. Here you go. So it has multiple outputs that produce the same waveform. So here's one of its outputs. Here's another one of its outputs. Here's the VDD output that I'm looking at. So it seems like when it comes out of this particular IC, perhaps it's on a 3.3 volt rail and no longer on a 5 volt rail. Here's the input. You can see it's quite nice and big again. So that's not an issue. I guess at least we know that the clock and VDD are getting to the FPGA. The next thing is to make sure the clock and VDD are indeed getting to the processor, and for that I'm going to have to find out which pins to look at. So we can do the same thing here, and one of the things to look for here is that I can actually look at the clock out, because the clock out will tell me that there is definitely clock inside the IC and being distributed and provided out of the clock out of the microprocessor. So I've located that pin. It's the pin all the way over here. If I plug it, what do I see? There we go. No, not bad. still has the clock coming out of it. So it looks like the microprocessor definitely has VDD and clock going in and out of it. That's already a good sign. So which means that hopefully there's something running on the microprocessor. Again, I suspected this because we were seeing that message on the display. Otherwise we wouldn't have seen anything. Something is active, something is running, and I suspect that again the microprocessor is responsible for loading the firmware, so it's displaying that message over there, and it just doesn't get past that point. And as I was mentioning, it could be because the flash memory is bad. So the next thing to look at, which were the point where I think is failure has happened, is on the flash memory and on the SRAM. And for that, I'm talking about these guys. So again, my hypothesis is that this guy has some interaction with the FPGA, grabs the firmware from the flash, loads it onto the SRAM, and then begins execution. That seems to be the cycle. And it looks like it's stuck somewhere between loading it from the flash or putting it onto the SRAM. So I have the SRAM pinout and I have the flash pinout, and we're going to do some monitoring, see what they look like. So what pins do I want to look at on the flash memory? Well, this is upside down because this matches the orientation of the chip that's on the board. So sorry about that, it just makes it a lot easier for me. And then the camera is in between me and the board. It's very difficult to do this. But anyhow, so here's a bunch of address bits here. Here's write enable, here's VCC, a whole bunch of more addresses here. Here's the output enable and the chip enable pins. These will be interesting to look at. A whole bunch of data pins and more address pins. Well, I want to just randomly look at some of the address pins, output enable pins, and perhaps one or two of the data outputs, because if there is some data output, at least something is coming out of this memory, of this flash memory, and that would be a good place to start. So I'm going to just focus the camera on the scope, and I'm going to tell you which pin I'm probing, and then you can kind of get an idea, and hopefully we can debug this from there. So let's go ahead. I'm going to first take a look at output enable. So the output enable should have some activity on it because obviously it's going back and forth between the two flash chips, and it should enable and disable that output. So I'm going to look at the first one. There we go, that's not bad. Again, the output amplitude is not as high as I want. It's a little bit weird that the signal digital values keep getting different values from different locations. But you can see a whole bunch of activity. Again, if I take a single shot, let me just zoom out again, take another single shot. You can see a whole bunch of activity. So that's normal. That's what we expect to see. So there it is. That looks fine. Let me look at the other chip. There you go, simple, similar thing. Let's look at one of the addresses. Let me look at address A11, for example, as a test point. There you go, you can see activity on occasional activity there. So it is, and look, the signal is so much bigger. I don't understand why the address bits, this is what's now beginning to worry me, because the address bits are definitely coming either from the FPGA or for the microprocessor, and they're full swing. But then when I look at the output enable, it's smaller. I would expect the output enable to come from a similar source, but its swing is smaller. So either something is dead and is loading yet, so its signal amplitude is smaller, or this is just the way it is, and they've designed it for different power supply voltages, and something over there is running at 3.3 volts. A little bit unusual, but anyhow, let's look at some of the data outputs. I'm just going to randomly pick a data output here. Let's see, I'm monitoring here one of the data outputs. Yeah, that also looks okay. Again, goes up to 5 volts. This behavior is interesting. This could be because it's an open collector, or because there is some high impedance output that's charging slowly, and then there is some output enabled kicks in and then discharges it. That could be from that. It's also an interesting behavior again. So it looks like there is interactions, at least coming from the flash chips. So let me turn my attention now, do a couple of similar things. I'm going to do the same thing now on this chip here, and I have the pin out of that as well. I'm going to go ahead, again it's upside down, I'm going to go ahead and take a look at some of these pins. So I'll tell you what it is I'm probing. So on the left SRAM cell, I'm going to look at the VCC. There you go. It seems like everything is VCC is 5 volts, which makes it even more interesting that the voltages don't match. So here is address number 15. Looks good. It goes up to 5.5 volts, so 5.2 volts with a little bit of an overshoot. So that's good. So that you can see the address 15. This is the last address, the highest address. So its activity is actually less because you don't often hit the last address on a memory. Let me take a look at the chip enable, which is the third pin. There you go. Again, similarly, the output signal is not as high, but you can see that it is indeed being enabled occasionally. Let's take a look at its, some of its IOs. Let's look at the last IO. There you go. This also has a similar thing. Yeah, so this is beginning to now worry me because this is very large. I wonder if this is because this SRAM cells are not working properly or they're damaged. But that's some activity again coming out of the SRAM cell. So that looks good again. Let's try another pin. Let's try the output enable. Let's see. And I am looking at... Sorry, I'm having some trouble. There you go, here's another I/O chip. And I'm seeing constantly the same issue with the different voltages appearing. I wonder if that's because one of these components is dead and it's loading it. Let me monitor some of the FPGA pins. That's sitting at high. Oh, here you go. There you go. See, here's one FPGA pin. One of the FPGA pin is high, sitting at 5 volts. The one next to it is sitting at 4 volts, which means it has to be loaded. That's the only reason why the digital output signal voltage will not be the same. Or it's an input coming from somewhere else that's not giving it a complete voltage. Here's another one. I'm just slowly going through all the pins here. And I can see various activity. I don't see any activity on the FPGA so far. There you go, there's some activity. So that's one of the pins obviously going to either the memory or the flash. Here's another pin, again another activity, digital activity. High, this is high. These are all just high. Here's our clock signal. Here's another one. Some 4 volt signals which are again low in amplitude. So something here is generating a low amplitude. Oh, you know what I'm going to do? Here's one thing to try out. I have two sets of memory here. Now this is the backup RAM, and it looks to me that this is where the loading happens, and this is some kind of a extra memory that's not being engaged all the time. So what I'm going to do is I'm going to compare an identical signal from all of these 4 chips and see if one of them has the high level and one of them doesn't, because I have many different chips here. Some of them do not share the same line, so therefore I should be able to tell at least if the output signal that I'm seeing is consistent between various ICs. So something interesting, I can look at the chip enable 2 of these 4 ICs, and there is a pretty interesting difference between them. Let me show you. So let me go ahead and turn this back on and turn this guy back on. There we go. So I'm going to look at the chip enable of the IC on the left. And this is what it is. You can see that it doesn't go all the way down, and its maximum voltage is 4. So it doesn't reach all the way down. I'm going to go to the chip enable of the other 2 SRAM cells. And look, it does go all the way up, all the way to 5.5. So something seems to be loading it. And I found out that the chip enable signal is coming from the FPGA by just looking at some continuity. So I wonder if this is because these SRAM cells have died, and they have some low... the I/O pins have died, and they're basically loading the digital output driver of another IC. That's one possibility. And the SRAM cells are reasonably easy to replace. So I'm just tempted to go ahead and replace them intuitively, and I think that might be one of the issues why the firmware can't be loaded. So let me go ahead and see if I can find a replacement part for these. These must be, surely must be obsolete. So let me see what I can find. So I did a whole bunch of search. Man, these are not easy to find. Eventually I found a bunch of them from one store, but they were selling them for a crazy price, something like $15, $20 each, and you had to buy a $100 minimum order. But I did find someone on eBay who has them. So I'm going to go ahead and buy 2 of these and try and replace this. Now it's just a matter of a waiting game until the new parts arrive. And here we are, the parts arrived, but they didn't come in an anti-static bag. They just came in this plastic bag. I can't believe it. I mean, you gotta put this into an anti-static bag. These are CMOS chips, and oh well, I hope they didn't die already, but at least we have 2 supposedly working ones. So one of the things I'm gonna do is I'm gonna remove the old ones, and then we can still probe the pads and see if the signals are bigger than they were, and then go ahead and put these on. So let me just go and replace those, remove those ICs, and that part is boring, but let me remove them and we can take a look at the pads afterwards. Well, guess what I did? I was watching Family Guy or listening to Family Guy in the background while I was doing the soldering, and I wasn't paying attention, and I went ahead and I installed the new ICs on before before the probing that I was intending to do. So I apologize for that. So we missed that, and now the ICs are on there, and here are the old ones you can see that I took out, and they're still intact, but I'm not sure if obviously they're alive because I haven't turned it on yet. And what I also did is I turned the screen around a little bit like this, so that when we go ahead and probe it afterwards to see if there's still any issues with it, then we can see the screen at the same time, because I thought maybe something was happening on the screen and we were missing it because it was on the side and I had no access to it while I was fiddling around and probing it. So this way we can take a look. So let's go ahead and turn it back on and we can do some more probing, see if the problem is resolved or not. Let me see, I don't see the light anymore. Oh, of course, because the power supply is turned off. That should help. There we go, power supply on. Oh, there was a moment of flicker there, interesting. So let me go ahead and turn it on. Oh, not turning on. Oh, there it is. And wait a second. Oh, look at that, it comes back to life. It's a miracle of science. There it is. And so that indeed was the issue. So I guess the memory was bad. This is very strange. This is the second instrument I've fixed in a row that had a broken SRAM. It never happened to me before. So it's an interesting problem to solve. I'm not sure which of these two ICs is the bad one, obviously, and I don't want to go ahead and change them back and forth to find out. This PCB is quite old, and most likely some pads are going to come off. We were already good soldering, no need to do that. But there's something on the screen which I can't read from where I'm sitting. It says can't find the required number of measurement boards. Oh, well, of course, it's because it doesn't have the measurement daughter board that would normally sit there. So naturally, it's going to give an error like this. So the only way to see if it's completely fixed is to connect it up and put it back together. And unfortunately, the only way to really properly assemble it is to put this guy back onto the whole motherboard, back onto the chassis. So let me go ahead and do that, put it all back together, and then we can do some performance verification. I'm curious to see if it needs calibration or not. And I also want to talk a whole bunch about what are power sensors, and take a power sensor apart, as you know, to complete this video and give you more value since you're watching it, and tell you how this whole thing actually works. So this should be pretty educational and pretty interesting. So let's continue. All right, all assembled and put together. So as you're just looking at this screen, and this is the camera's reflection. So let's go ahead and turn this thing back on, and there you go. Now it's booting. Battery test. Calibrator passed, measurement assembly, come on, passed, there we go. So it's, well, it passed all the self-tests. Doesn't mean it's going to work yet, because I have to connect the sensor to it, of course, and make sure that it is, you know, all looking good. But I want to tell you first a little bit about how the sensor looks like, and take a sensor apart for you before we go ahead and verify the performance of this unit, which should be pretty interesting. So let's do that first. So a power meter is obviously useless without power sensor. So here are a couple of power sensors that I have in my lab that I use regularly for different applications, and I want to tell you a little bit about them. The first two are USB based ones. So these ones don't actually need a power meter because everything you need is already built into it. I'll talk about that separately. The two at the bottom are the ones where would be compatible with something like the EPM-441A or the other dual channel power meter that I have in my lab. And now that I have this new one, I have another HP based one, another EPM based one that can use these sensors. So let's take a look at this one. This is a fairly old sensor, the E4418A. It's a very popular model. This is a medium power sensor, so it works from minus 30 dBm to 20 dBm. As you can imagine, below minus 30 is below the noise floor of this particular model, and above 20 dBm would be above its linearity level. And it will get damaged if you put more than 300 milliwatt into it. And this one works from 50 megahertz to 26.5 gigahertz, and the calibration table with all the coefficients and so on are written at the back, and this is something that's done at the factory level, so printed for each individual one separately, and then you'd have to load this table onto the power meter so that when you set the frequency, it knows what correction factor to apply, and it gives you the correct power that you're supposed to read. Now normally for the newer models, the E-series power sensors, once you plug these into the power meter itself, the data will be automatically serially transferred, so you don't have to type this in. Otherwise you have to put it in manually. You can save it, of course, and unload it later when you switch sensors. So this is an old one that I've had for some time, but it's a fairly used, it's a regular power sensor for typical applications, because it has a nice 50 dB of dynamic range, right around 0 dBm essentially. So a very typical workhorse kind of power sensor. Here's another one that I have. This is my high frequency power sensor. It goes from 50 megahertz to 60 gigahertz. So it's obviously a much higher frequency one, and it uses a very high frequency V-type connector here, and it also has a calibration table you can see at the back here. This is also not an E-series one, therefore you cannot plug this into, you have to type the table back in there. This is an 8487D. These are much more pricey. This is a low power one, and it goes from minus 70 dBm to minus 20 dBm, and as a result it is not very suitable for high power applications. I usually use this maybe for radios and some very low power application, obviously down to minus 70 dBm. Which is very low, as you know. This is an Agilent one, so it's a newer model. But the thing that is very interesting, my favorite power sensors are these two that I've picked up from eBay actually fairly recently for an incredibly low price. I'm very happy with that purchase. This is a U2000A. This is a 10 megahertz to 18 gigahertz one, and it goes from minus 60 to 20 dBm. This is an 80 dB dynamic range power sensor, which is quite a lot. And again, it has this one is different. It has a USB connector, and it uses a special cable. I mean, you can use the regular USB cable, but there is a special cable that kind of screws in there to make it nice and stable, and it even has a trigger port, so it can trigger on a particular external event. So if you want to catch a very short pulse, you can do that. But with the new firmware of these ones, you can actually catch the pulses directly with the internal DSP, which is a very nice feature. Maybe we'll do some experiments with that some other time. And the other one that I have is for very high power applications. This is from minus 30 to 44 dBm, which is a lot of power, and it works all the way up to 6 gigahertz. This one is essentially intended for a cellular application, cell tower application, and consumer electronics that put out a lot of power in the 2.4 gigahertz or so. This one requires an external attenuator, so there's a 30 dB attenuator. This is not the one that came with this unit. There's a really big one with a big heatsink that is shipped with this unit, but that wasn't available when I bought it on eBay, and I just picked up one of these 30 dB 50 megahertz reference attenuators. This is not going to be very accurate because it was calibrated with the big external attenuator, but nonetheless it's a fairly nice unit, and we can use this. So this particular one is remarkably well calibrated. I tested it. It's very close to being essentially perfect, down to below 0.01 dB. So we're going to use this to check the calibration of the unit that I just repaired. But having said that, well, how do these things actually even work? How do you detect the power? Well, there's two different ways the power is detected. Either it's done by the square law region of a diode, so by rectification, or by thermal effects through a thermocouple. So I just printed 2 pages here, I put some diagrams together. I want to explain how this works, because if you're going to go through all this, we may as well learn exactly how they work, and I can explain it to you, something that I've been wanting to talk about for a while. So let's take a look at that. So as I said, there were 2 ways of detecting RF power. One was using a thermal temperature effect, and the other one using diodes for rectifying. So here's a special type of semiconductor here that uses tantalum nitride on one side, separated by silicon oxide, which then when exposed with RF power creates a gradient of temperature, and that gradient of temperature can then be picked up and then amplified and measured. So there is the temperature gradient developed in this type of semiconductor is going to be proportional with the RF power, and with a proper calibration curve, you can go ahead and take this semiconductor designed piece here and connect it on 2 different points where you can have a hot and a cold junction, and then you can have it an N-type silicon on one side, and then switch it to the other way, so you can have a reference measurement point and one point that's actually exposed to the RF, and take the difference and go to a multimeter and then measure essentially the power that's coming in. Now this thermal type of detectors, I'm not sure how often they are used anymore, because as far as I know, most of the time the diode based ones, the rectifying ones, are typically the ones that are used. But this was a very popular type of power detectors, and perhaps one of the ones that I have might even be, I haven't checked all of them, but I'm certain that the USB based ones do not use this method. So what about the diode based one? Well, that one's actually quite a bit more straightforward, because if you go ahead and write write the exponential IV characteristic at a diode, of a diode in terms of a power series expansion like this, you can see that there is a term that's proportional to the square of the voltage, and the square of the voltage is, of course, will give you proportional to power in watts. So if you run these diodes in square law detection mode, you're going to be able to get a voltage out of them that's proportional directly to power, and that's exactly what is happening here. So what they do is that they have two diodes back to back like this, which are one of them is swapped, and they give you a plus and minus voltage differentially here to reduce common mode effects that appear on these diodes. And by running these diodes in the square law region, you're going to be able to do the rectifying and get a voltage proportional to the input power. But of course, there is a dynamic range limitation because you're not going to be in the square law region for long. Eventually, you got the fourth and the eighth harmonic are going to become significant, and then you're not going to have the square law. You're going to have quasi-square law detection, which is going to throw away the curve, and you're not going to be proportional to power anymore. So what they do in that case is that they have a situation where they are able to attenuate the power by a certain amount, and then connect it again to another pair of diodes. So this pair of diodes will be the low power sensing, and this pair of diodes will be the high power sensing because they have attenuated the power. So this one will operate below its noise floor when this is working, and then this one will be turned off and disabled, and this one will be operating in square law region when this would normally be in the quasi square law region. And then they can switch back and forth. In the particular model that I have, from minus 60 dBm to minus 7 dBm is done by the low, and then the upper range, once you go from above minus 7 dBm to 20 dBm, they switch to the attenuator. I believe this attenuator is about 30 dB of attenuation. And that's how this particular one will essentially work. So they take this diode detection circuitry and they put it inside a little tiny computer, basically, which is going to look like this. So here is our four diodes with the attenuator in the middle. So here's one path with the attenuator here. Here's the low gain path. It's just drawn slightly differently. They have put two diodes in there, and I believe they have done that because again, to increase the power that this one can take by putting two back to back to keep it in the square law region even further. That's what I believe is happening here. And there's a switch that selects the high path and the low path and so on and on. And of course, there's a differential chopper which is used to drive a low gain amplifier and a high gain amplifier, and this combination of the chopper and a low and a high gain amplifier ensures the proper placement of that voltage within the optimum dynamic range of the ADCs, the 14-bit ADCs that follow, and the signal then is taken from the two 14-bit ADCs sent to a 16-bit DSP processor that does all the computation, calibration, and does all the fancy things that it needs to do, has some flash memory, has some SRAM memory, and this is quite fast, and it has peak detection and all the stuff that I told you, and the trigger circuitry is processed by the DSP as well through this path, and there's some power supply, USB 2.0, blah blah blah. All that stuff is fairly straightforward. And at the same time, there's a thermistor here. That thermistor is sitting right next to these diodes to continuously monitor the temperature of these diodes and send that data through another ADC back to the DSP to continuously compensate the temperature so that your ambient temperature doesn't affect your measurement. Remember that these diodes do have the thermal voltage 25 millivolt as part of the equation of the exponential, and any temperature change in there is going to affect the junction voltage, and of course going to drift away the power you're trying to measure. So that's very critical that this is temperature compensated for continuously in a loop, and indeed that's what's happening, especially because the RF power coming in is also going to have thermal effects on these, and so on and on. So this is the block diagram of something like this, and now I hope that you have a fairly good idea of how this thing works, and now you know what's going on inside it. I happen to also have a broken one. This one I took the casing off because I was curious to see what's going on here. This was a very good this was the E-series that I was talking about. As soon as you plug these E-series in there, they will automatically become, it will be downloaded into the calibration coefficient table that, oh, actually it's not written in the back, it doesn't need to be, but the calibration coefficient gets sent onto the power sensor and then power meter, and it gets automatically calibrated, so you don't need to worry about the table. I found this actually in the garbage because it was completely dead, so I picked it up simply because of my curiosity. And look at this. Minus 70 to plus 20. That's a 90 dB dynamic range. It's as much dynamic range in a power sensor that I think I have ever seen. So this was a very, very good unit, and someone has killed it probably by putting way too much power into it. So I can go ahead and take it apart. The construction is pretty interesting. You can see multiple layers of shielding built into this guy here, this can, and this can has You can say this as a very static sensitive assembly in here. We'll take this apart so we can take a look at it, but obviously these are diodes, so therefore it is static sensitive, so you have to be very careful taking it apart. This one's dead, so we don't care. And he has the connector, the proprietary HP connector, which all the other sensors share. For example, this is the one that I have that works. Here's the 50 gigahertz one, which also works. All have the same connectors. So this has a couple of Allen type screws, I believe, on it. So I'm going to go ahead and get my screwdriver to open this. We can take a look at it. Here we go. I took all the screws off, and now this panel will come out. You can see it here, the construction of it, quite a thick piece of metal here, and obviously specifically designed for this. And now you can see the internal construction a little bit better. So here I actually, now that I opened this, I remember I've opened one of these before many years ago. When I looked inside, I remembered. So you can see that the cables coming out of the detectors here, the diodes there, and there is an almost like an elastic band in here which keeps the cable in place. It's a very interesting construction. You can see I can take this elastic piece off here, then it just slips off, and that is just so you can keep this piece of almost like a ribbon cable in place. And I'll take this apart further. There's obviously no A to D conversion happening here, I don't believe, and this is just some signal conditioning, power supply conditioning to power the diodes and so on. There's a bunch of equipment and components in there. You can see all these are actually glued in place, because if you drop this, you don't want these to bang around and mess things up. So let's go ahead and take these two screws out as well, and try and hold things as steady as I can so you don't get a headache looking at it. These are pretty long screws. There's one and the other one, and you can see that the way the diode actually connects to the power supply is just by the pressure from this particular connector. There is no solder point, there's no solder joint or anything like that. So you can see if I go ahead and remove this, and this piece here is specifically designed to push that little cable onto the PCB. So there you go. You can see a closer look. I should be able to take this ring out now. There it is. It's a little rubber band style, and this the cables here coming from our diode pushing onto those PCB traces right there, and that's why that whole assembly was to protect. And there's some capacitors, it seems, bypass capacitors there, or I should say AC coupling capacitors there, that isolate the DC connection and so on. That's what I believe is going on there. So we should be able to even take this apart further. There's a screw in here. There we go, and that completely separates this assembly from this assembly here. So let me get that screw out here so you can take a better look. There you go. Now there's nothing fancy going on here. I'm gonna go ahead and further open these screws. I'm gonna don't really need this power sensor anyway. Like I said, it was something that was found in the garbage. Now these are not really repairable. If the problem was with the electronics, then yes, that would be repairable and I could replace it. But I know that this one has a dead sensor, so the only way to repair that, there goes some more components here at the back of this. Let me see if this can focus on here. There you go. What am I looking at here? I don't immediately recognize what this one is, but anyhow, there you should be able to read it. So you can go ahead and decipher what these components are. I don't want to spend too much time on it so that bore you guys, but it's useful to keep these connectors and so on for future, maybe something else. This board is most likely functional, so if I find another power sensor one day that has a dead board, then I can replace it. But we know for sure that I don't believe that I should be able to fix this. But you can see all this handwriting stuff on it from basically the person who assembled it and characterized it and give it a serial number and so on and on to make sure it's working. It's a type N connector there. So let's go ahead and further disassemble this. It should be interesting to take a look at that RF connector. So something I didn't mention, you may ask, well, why would you ever use a power sensor anyway? Because you have a spectrum analyzer, you can just measure power from there. And the reason for that is that the spectrum analyzer is not very accurate in measuring power. It has an amplitude uncertainty of about 1 dB. The power sensors have an amplitude certainty of less than 0.01 dB, so they're extremely accurate. Furthermore, as you can imagine, with the square law detection, you cannot discern the frequency. If you have a complex modulation, a complex spectrum, it's going to integrate all the power together. So you're getting the power of an entire bandwidth from 50 megahertz to 50 gigahertz here. And that's another reason why these are interesting to use. So they behave a little bit differently, even though when you're using a spectrum analyzer, you have all kind of different detection modes also, but mostly the accuracy and broadband nature of this is why they're used. So anyhow, here we go. I've gone ahead and taken this apart. So this is actually a 3-section piece, and if you're going to go ahead and take a look at this, and I can disassemble it piece by piece, and you can see how it works. Ta-da! And you can see bits and pieces of it. So here it is completely hollow. This is a center pin of the type N connector, and this center pin of the type N connector ends in this way. And this piece at the back here, which I'm trying to get to focus, is just basically a 50 ohm pin in the center, surrounded by the conductor that's here, and that pin touches the top of that particular assembly, and that particular assembly can be taken off as well. Oop. There you go, so something just fell out of it. One of the washers came out of it, and this has yet another piece, and this piece will separate. Just so much beautiful microwave engineering. And here's the top of that pin, so this guy will be in touch with there. By the way, if you disassemble this, the calibration of the sensor is gone, because the interface, the way these two were connected together, and the exact pressure, you can see the spring nature of that. You see? That's how they ensure good RF connection between them whenever the whole thing is assembled. Just so beautiful, these things. And you go ahead and take it further. Here you have another similar piece, and at the bottom of that is when it comes in contact with essentially the assembly of the diode that is all the way in there. And we should be able to take that apart as well. That is, if I can figure out exactly how. Most likely this thing can be opened. So let me go and wrestle with this, see if I can take it apart further. Here we go. I just loosened this, so now you can take it apart further, and you can immediately tell why that gap is there now. That gap is there obviously in order to allow the cable to escape and come out. Ooh, look at that. There we go. So again, another hollow piece in there. All these are, well, there goes something. There was a pin in there that just fell out. Oh well. And here we go. We can take this apart as well. Let me straighten this piece and gently take it through this gap if I can. There we go. So again, another machine piece, and here is our diode assembly piece. There you go. And this is a piece of plastic that can come out. Look at that. That is cool. Sorry, I wasn't sure if you can see it. That is very, very interesting. Now I am very tempted to see if I can disassemble this even further and look at under the microscope. Yeah, let's do that. Let's try that. Here we go. I've placed the part right here under my Dynolite microscope here, and you can see the image here on the computer. Sorry that I'm filming the screen. It's just much more convenient for me to quickly show you. So here are the 4 cables that go onto the ribbon cable on the side that you saw earlier, and they go onto this little board that's housed inside the brass container. And here you can see the 4 multiple traces. Here's some bond wire here, some bond wire here, and one here. You can see some number, a part number perhaps. And then there's 2 other traces that go underneath this main brass piece, and the RF signal is actually coming from this side, and the cable is going out from that side. Now, the reason I couldn't take this out before was because you can see that there is epoxy in there. So they've likely put silver epoxy or perhaps some solder on here first, slid it in, and then baked it. So that way the edges of this, which most likely are ground, so this must be ground, and this bottom plate of this must be ground, and those ground plates are soldered essentially onto the brass container. That's why I couldn't take it out. But nonetheless, what I'm going to do is I'm going to heat it up and see if I can take it out. If we destroy it, then we destroy it, but I'm curious to see what's underneath there, and I want to put it back under the microscope. So let me try a bit more, see if I can take it off, and if not, that's still okay. We still got to see something. Check it out, success! I took it out. It actually came out very, very nicely by heating the plate and slowly pulling it out. It actually came out quite nicely, so it was obviously epoxied in place. So let's put it under the microscope. And here we go. Look at it. Look how beautiful it is. This particular one, you can clearly see what's happening here by taking a close look at it. So Here's where the RF signal comes in. You can see the RF signal comes in really wide with ground planes separated quite a bit. Let me go from this side. And through this transition, you can see this is a coplanar waveguide. Bringing it in, it maintains a 50 ohm impedance going onto the diode detector right in the middle. And here's our differential output of the diode coming out. This is one capacitor, this is the other capacitor for the rectifier. This is a DC coupling capacitor, I believe. And this pin right here, this one, so this would be biasing the diode. This is ground. You can see it goes underneath the capacitor and connects to the side and creates a good solid ground for the coplanar waveguide. And here's are the two differential outputs of the diode. The rest of the circuitry that are in here is going to be the EEPROM, the chopper, and all that stuff is going to be, of course, directly in here. And you can, if you were to follow these traces, we should be able to follow exactly where the signal goes. But we know we can do that. Some of the time it's not that important, but I really wanted to take a look at Detector. So this ended up being a pretty cool video so far. I really enjoyed taking this apart. I had never taken one apart all the way to this level. I've only taken it apart up to the circuit. So it's really cool to see the detector. Now that I see the diode in there, if I had a wire bond machine, potentially I could go ahead and replace the diode if I had a replacement. But by getting to this point without damaging anything is promising, meaning that these are, in theory at least, repairable. Pretty cool. So now that we know so much about power sensors and power meters and how they work and what the block diagram looks like, it's time to go back to the unit I repaired and see if it works, and if it's calibrated. Let's measure its output power and so on. Should be still pretty interesting. Here we go, and I cleaned the unit front and back and everywhere. There's a lot of stuff on it, marking on it, and I also took the calibration sticker off, which was last calibrated in 2006. That's quite a long time ago, so I'm curious to see how well it is calibrated. And what I'm going to do is, I have actually connected to this power sensor, which I didn't show you earlier. It's a really old one. It's an HP-8481A, but it's in a very good shape. So let's go ahead and turn this thing on, and it should detect the power sensor. Here we go. It does the self-test like it did before. Blah 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 blah, and there we go. What is it doing? It should detect our power sensor. Please zero and cal. Okay, I guess it's asking me to zero it and calibrate it first. I can do that. Here's a 0. There you go. It's zeroing it. It must be set to force you to calibrate and zero. I'm going to change that. That's pretty annoying. So there you go, I just zeroed it and now it says please cal it. Alright, we'll cal it. So I have to take this off now. Let's go ahead and connect this guy in. Anyway, at least this way we can verify that it does the calibration. Even though it may be wrong, but at least it will go through the procedure. Oh man, this is a difficult connector to put on when you're behind the camera. There we go. Alright, calibrate. So what it's going to do is that it's going to apply the reference 50 megahertz 1 milliwatt output, and it's going to zero. There you go. It did it. So now you can see that it says minus 36 dBm because there is no output power. Now if I go ahead and, oh there you go, this is what must cal. Let me turn that must cal off. That's annoying. If I go under system, if I go on second page, I should be able to turn the output on. How do I do that? Let's see. There is a way to actually force the output calibration to be turned on. There it is, power reference on. So I can turn the power reference on and off. So if I turn the power reference on, now you can see it will say exactly 0. That doesn't mean it's correct because it's just comparing it versus its own calibrated power that it put out during the calibration procedure. So I hope you can see this, by the way. I assume that you could, but there you go. So you can see now it says 0 dB, and if I go ahead and turn the power cal off, it's going to go to the noise floor. This is a minus 30 dB noise floor part, so you can see it's just below that. So if again I can turn it back on, it should go back exactly to 0. Now, what is really important to note is that, like I was saying, if the reference calibration power is not 0 dBm, then this is just, it's going to assume that it is, and it's just comparing it versus itself. That's why it says 0. It doesn't mean it is correct. So two things I want to check. I want to first check to see if this signal is at 50 megahertz, because it should be very close, and because the 50 megahertz is the calibration point of all the sensors. That's the standard reference calibration frequency, so that's one thing we're going to make sure. So in order to do that, I have it connected here to my universal counter, which I've used in some of my other videos, and it should be the counter should be fairly well calibrated. Here we go. There we go. This is connected to the HP441A and connected to channel 1. So I'm going to go ahead and see if I can enable once again this thing, and let's see what we read. There we go. Look at that. Not bad. There. So it's reading 50.2 megahertz. So I think the calibration should be plus or minus half a megahertz. So it's pretty close, I think. So it's 50.2 megahertz is good. I wouldn't worry about it. I am too lazy to adjust it. That's not going to make too much of a difference. What is more important is that the power coming out is indeed 0 dBm or 1 milliwatt. In order to check that, I have to check it with a totally independent power sensor, which is calibrated by another calibrated 50 megahertz reference. So like I said, my USB power sensor is very nicely calibrated. So I'm going to use this guy connected to USB to the computer, and you can see this is the USB cable connected to it. I'm going to use a U2001A, which is nicely calibrated, to check, make sure that this is 1 milliwatt. And if it is, then we can declare this repair a success, and yeah, and I think that would be pretty awesome. So let me go ahead and switch the setup and take a look at that. And here we go. We're going to check the calibration of this guy, and everything is set up. You can see I have connected my power sensor to the computer, and there it is, and you can see that it's running. This is actually remote desktop onto my actual desktop computer. That's why it sometimes is a little bit slow, because it's going over the air here. So there we go. Go ahead. I'm gonna try to have both of them in view. I don't think that's possible, but let's go ahead and turn it on. And oh, look at that. Oh, it's so close. There it is. So it's reading minus 0.01, which is really close, and it's within the calibration limit of actually this power sensor that I have. So yeah, you know, I would increase the power maybe just a tiny amount, but anyhow, I can always do that later. There's nothing special about it. You saw it was just a potentiometer inside. You just turn the potentiometer and then you can increase the power. So it looks like it is indeed fully functional, and it is working. So another successful repair, I would say. So I'm going to go ahead and put the legs around it. I actually found another handlebar that I had, so it's going to look like a complete unit. And I'm going to go ahead and replace my really old one, which I'm going to actually briefly show you, because I made a modification to it to tell you which one I'm replacing in my lab. But anyhow, let me grab that. So this is the unit that I'm going to replace. This is an HP437B power meter, really old one, which works perfectly fine. You can see it has all the similar interface here, this is similar proprietary connector. Here's the reference 1 milliwatt output. The interface is quite the same. It's a very small LCD screen. Now I also have in my lab, as you've seen in other videos, an E4418B, which is a 2-channel version of this, and it's a B, not the A, so it's the next generation. But now this is a much better unit than this. The reason I wanted to show you this is because the screen on this is actually quite dark, because there is no backlight, and so is this, so you cannot see it when it's dark. So one day when I was kind of bored, I decided to install a backlight on this. So it looks like this now. And I did that a long time ago. So if I turn some of these lights off, there you go. You can see that now you can really read it when it's dark. So I think this is the only one that I've ever seen that has a backlight. Anyhow, I'm going to go ahead and probably sell this because I don't need it anymore, and sell one of my power sensors that I no longer need. But anyhow, so this is gonna go out and it's gonna get replaced by this again, and I think it's a nice repair, and saving instruments from the landfill is always a good thing. So I hope you enjoyed this video, and it was a long tutorial. I certainly enjoyed making it. So if you liked it, please take a brief moment, write a comment, and rate the video as you see fit. It always helps. The ranking allows other people to be able to watch the videos and be exposed to it, and this is for education, so it should be pretty interesting for anyone. All right, until next time.